Hi everyone, welcome to a new video. My name is Roni and today we're going to talk about support vector machines. This video is the first video in a new course called Supervised Learning, and I'm starting a new series, like a big marathon, 100 days of data science, and course 1 will be focused only on supervised learning, where we highlight classification and regression use cases, and now we are starting support vector machines. So in this video, we will cover definition of support vector machine, or for short SVM, the main characteristics, when SVM has limited performance, when SVM is not your best algorithm, how to distinguish between soft margin versus hard margin, and when to use each one of them. And we will focus on kernel trick. So kernel trick is mainly when we have non-linear data, raw data, and this data has a high dimensional and quite messy and complex. So in this case, we use kernel trick because support vector machines is designed inherently for linear data. And we apply that kernel trick. There are many methods for that, but we will focus on the 3 common methods of the kernel trick to help us solve the nonlinear, complex, high-dimensional data. And we will conclude with the SVM common interview questions to help you solidify all the techniques and methods, strategies we have used in this video. But before we start, don't forget to like, subscribe, comment, and share, and let's dive in. And let's start with the support vector machine definition. It's a versatile algorithm used as a classifier and regressor predictor. In classification cases, we use SVM as binary classifier or multi-class classifier. SVM, or support vector machines, is used in areas such as linear and nonlinear classification, linear and nonlinear regression, novelty detection, and anomaly detection. But also need to remember that in classification cases, SVM outputs a decision boundary or a score rather than a probability. Here you can see SVM graph. We have x-axis that focus on class 1 and y-axis that focus on class 2. Hyperplane represents by the bold black line, and we have support vectors. Support vectors are the points or data points circled in green, small green circles. We have also boundaries, margin, the dotted black line. And finally, margin that represents the white space between the 2 dotted black lines. When to use SVM? When we have small to medium-sized data set, regardless of the number of variables. SVM model generalize well while training with a robust performance. SVM works with linear data, and in case of nonlinear data, we rely on kernel trick. And when dealing with SVM, ensure to apply feature scaling so the decision boundary is well defined. As you can see in the graph on the right, we have the 2 line plots, the first one with unscaled data points, and the second one when we have scaled data points. Also, you can see that on the x1, the y-axis, it goes on the left line plot, it goes from 0 to 75, but here on the right side, we goes between -2 to +2 data points. And the same thing with the x0 on the x-axis. We have on the right line plot data is between -2 to +2, and on the left line plot it goes from 0 to 6. I highly recommend to check hands-on machine learning with scikit-learn, Keras, and TensorFlow. It's a great book that highlights many algorithms. I will leave the link down below. And SVM limited performance. SVM is hard to understand and interpret. The results is what I mean here. That's because SVM is one of the black box algorithms. Also, it doesn't inherently provide feature importance metric. So instead, we rely on applying permutation feature importance, strategy to estimate the feature importance indirectly. And finally, SVM is quietly slow with massive data sets. Then we have the kernel trick. I wanted to visualize it before we break it down and define the definition and types, etc. So here we have two scatter plots. On the left side, we have the scatter plot before making any prediction. As you can see that the data points are not really suited or fitted in one line. So if we try to use linear simple linear regression, it won't fit here because it won't capture all the data points. Instead, after applying polynomial kernel, one of the most common kernel methods, it fitted most of the data points. So here I wanted to visualize how kernel trick methods work on the live data points. Kernel trick, as a definition, when we have data or raw data that's not linear, it's complex, uncleaned, unscaled, and requires a lot of tuning, we apply kernel trick. And we have four commonly used in data science tasks: linear kernel, polynomial kernel, sigmoid kernel, and Gaussian, aka radial basis function, RPF for short, kernel. In this video, I will only focus on the linear Gaussian kernel, polynomial kernel, because sigmoid kernel is rarely used. So just focus on the main points, then we can go further if we need. If you want me to make a video about sigmoid kernel, I can make a short video about it. Just add the comment down below. How to choose the right kernel? I have to find in two questions to help navigate this many methods. So start with, are you worried about the computation performance? If the answer is yes, then choose linear kernel. The second question, is the data nonlinear with complex dimensions? If yes, then go with the RBF kernel or polynomial kernel, depends on the practical use case you have. We're starting by defining the linear kernel. So this is the most straightforward method, best suited linear separated data and data that doesn't need data transformation upfront. It's also efficient with massive data sets where computational speed is a priority. Classic use cases here that are text classification, sentiment analysis, like document categorization, and genomic data processing. And you can see a screenshot of the code on the right. We have imported the SVM. Then we choose the kernel to be linear and then fit the model and train it. Then we have polynomial kernel. So polynomial as a word, it simply means we use math with multiplication and powers. It allows more complex decision boundaries so we can have separable classes. That's what polynomial kernel is. Classical use case here is image processing, some certain financial forecasting analysis. We also use polynomial kernel. And you will see on the right side the screenshot that we have defined the kernel to be poly, short for polynomial, but there are a new element, degree equal 4. Degree of the polynomial is typically small. And here I wanted to visualize polynomial kernel. On the left side, we have scattered data points that are 2D. And you'll see that the blue dots and red dots are circled in one circle. And it's quite difficult to add a linear line or hyperplane line to distinguish between the two classes. It's quite complicated. So here on the left side, the flat paper, the blue dots are trapped inside a ring of red dots. And no matter how you draw a straight line across this flat page, you will always mix up the colors. So it's inseparable. On the right side, we have the magic hell. This is the polynomial kernel. Play a great role here because it uses math to lift the inner blue dots up into the air, forming a hell shape. Now, a flat orange chopping board can slice right underneath them and completely separating the blue dots from the red dots by the orange board. And then we have the RPF or Gaussian kernel. So it measures how close two data points are to each other using Euclidean distance. when complex raw data with high-dimensional features is completely messy and nonlinear for both classification and regression cases. We usually also apply hand-in-hand grid search and cross-validation strategies on this kernel type. And as you can see here on the right side, we have the kernel is defined as RPF and gamma is 0.5. Let's break down the two main features related to RPF kernel. We start with the C parameter or regularization. So C parameter for short controls the penalty for misclassifying training examples. A high C parameter tries to classify all the training points correctly, risking overfitting, while a low C parameter allows a smoother margin with some misclassification to ensure better generalization and overall AI model performance. And then we have the gamma. So the gamma simply means controls the shape of the decision boundary by defining how far the influence of a single training example reaches. A low gamma means a wide global influence, smoother boundary, while a high gamma means localized tight influence, potentially leading to overfitting. Of the tuning kernel performance, it's a great to establish how to get the best of the kernel in order to get the best of the SVM overall performance. We have many ways we can use it to enhance our kernel performance. The first one is grid search. Systematic testing of parameter combinations is conducted to achieve optimal accuracy. The second strategy is cross-validation. The data is repeatedly divided to assess the strength of generalization. Then we have regularization control, C parameter. The penalty settings are implemented to avoid overfitting in high-dimensional spaces. Then we have the gamma control. This helps to smooth the decision boundary while preventing the model from overfitting or underfitting. And finally, the degree adjustment. In polynomial kernel, the complexity of the polynomial is modified for smoothness, controlling the number of dimensional combinations to prevent an explosion. We are with the final idea in this video, how to distinguish between soft margin versus hard margin. So soft margin helps in maximizing the distance between the margin boundaries. Asn introduces a penalty term, the C parameter, that allows for controlled trade-off, tolerating a few misclassifications in return for more generalizable margin that leads to robust model. Then we have the hard margin. It also helps in maximizing the distance between the margin boundaries as it aims to find the weight vector and bias term that maximize this margin while ensuring that all data points are correctly classified. So we can conclude here that soft margin is more flexible with the data points, unlike the hard margin. Both margins aim to maximize the distance, the width, between the two margin boundaries of the street between the support vectors. However, the soft margin introduces a penalty term, C parameter, that allows for a controlled trade-off. It means accepting a few misclassification in exchange for a wider, more generalizable margin. Remember, our ultimate goal as a data scientist is not just to build a model that aids the training phase and fails miserably in production. We build models to generalize well, prevent rapid decay, and actually deliver real business value. Now with the SVM interview questions, my favorite. So we have here a few questions that challenge our full knowledge. First, explain SVM in your own words. Second, explain support vectors in your own words. Third, explain kernel trick with an example. Then explain how to choose the right kernel. 4, say you have trained an SVM classifier with RPF kernel, but it seems to underfit the training set. Should you increase or decrease gamma? What about C parameter? Explain in detail. And finally, why is it crucial to scale the dataset features while implementing SVM? So drop your answer to question 2, gamma versus C parameter, in the comments below. Let's see who gets it right. And that's it for today. Thank you so much for watching my video. Make sure to subscribe, activate the bell, comment, like, and share, and I will see you in the next video. Bye.